Hello, and thank you for joining me. My name is Matthew Mueller, and I'm the Manager of Education Innovation here at PTC Education. And today I'll be talking about how researchers and teachers are taking advantage of Onshape's cloud-native architecture in new ways in higher education settings. A quick note, please feel free to write in the chat and add your questions in the Q&A while I talk. I'm joined by my colleague Peter Zink, who will be monitoring those, and we'll try and answer as many questions as possible at the end of the session. So to quickly introduce myself, I did my PhD at Tufts University in mechanical engineering, where my research focused on designing learning environments to enable students of all ages, from pre-college to university level, to engage in real-world engineering practices. Now here at PTC Education, my role is to develop new ways for teachers and students to use Onshape. I also work directly with faculty members from around the world to support their research and teaching using Onshape. So I'd like to start the talk today by giving a little peek under the hood at how Onshape actually works and how it's fundamentally different than any other CAD platform. Then I'll talk about what the implications of these differences are for research and teachers. Then I'll highlight some exciting examples of how researchers are taking advantage of these new capabilities in the fields of deep learning and artificial intelligence, design process and education research, and digital twins and robotics. And finally, I'll highlight some of the ways that teachers are using Onshape to have their students engage in engineering practices that go well beyond the basics of computer-aided design, including collaboration, product data management, and computational design. And then we'll have some time for questions at the end. So to start, let's try and understand a little bit about how Onshape is different than other CAD platforms. So this architecture you see in this diagram is what you might expect from any traditional desktop CAD system these days. There's a CAD application that's downloaded onto your computer, and then there's some central file system that keeps track of all the parts and assembly files that an engineering team is working on. Everybody should be fairly familiar with the pros and cons of a setup like this, but the two drawbacks of this architecture that I want to specifically highlight are the need for a powerful workstation with high enough specifications to run these high-powered applications. And the central file system means that when engineers want to work together, they have to check the file out, during which time nobody else can see that file or their changes, leading to slow waterfall serial design processes. We're seeing traditional CAD systems start to embrace the cloud in a couple of different ways. One approach that we might call the hosted CAD approach is where you essentially rent a virtual machine running in the cloud, but ultimately you have all the same drawbacks of working with a central file system that you might see on a traditional desktop CAD system. The other approach that we're seeing is what we might call the thick client, where the CAD data is now stored in a central cloud database rather than a file system, but you still need to download and install a client to run on your computer. So you're still on the hook for a powerful workstation capable of running the application and keeping track of all version updates as they come out. Neither of these approaches take full advantage of the cloud, and that's where Onshape comes in. Onshape decided to start from scratch and build the first cloud-native multi-tenant CAD system from the ground up. With Onshape, there are no downloads required. The client runs directly in your browser, or if you're working on a mobile device as a lightweight application, and communicates with the distributed cloud architecture of what we call PTC Atlas, enabling more agile and collaborative product design processes. It's worth mentioning here that this cloud architecture was one of the reasons that PTC was so excited by the acquisition of Onshape. And PTC as a company is now leveraging this Atlas platform to bring the power of cloud to a number of other technologies in our full suite of products. But how has Onshape managed to build this cloud-native system? At the highest level, the distributed architecture is key to making sure that Onshape is accessible from any device and never crashes. But I would like to highlight two of the specific architectural decisions made early on that have opened up a number of new possibilities. The first is the database, which is the fully secure single source of truth for all design data being used by an engineering team. And the second is FeatureScript, a brand new programming language developed by Onshape for Onshape to specifically handle the language of CAD, which is parametric features. If you want to learn more about how Onshape really works, I'd recommend looking at the recording of a session earlier today titled Under the Hood, What Happens When You Add a Feature, that was presented by Ilya Barin and Lana Saxonov earlier today, two of the original architects of Onshape. So what does all of this mean for researchers and teachers? So to start, I'd like to flesh out that first architectural decision I highlighted, which is the database architecture. The way that they have enabled this widely scalable platform to work and keep storage costs down is by storing each edit as a flexible incremental change. This is also the fundamental decision that enables simultaneous editing, just like Google Docs for your CAD platform. This also enables the parallel workflows such as versioning, branching, and merging that enables more agile product design processes. Another feature of the database architecture is that each edit is always appended onto the database. This means that data can never be lost and you can infinitely restore to any earlier state. Another advantage of this is we now have all of the actions that each engineer is making over time, leading to exciting opportunities for understanding how designers are actually working together on CAD. And finally, Onshape's database assigns internal unchangeable IDs for documents, versions, tabs, geometries, etc., which means that references can't be broken. This also means that you can individually reference any aspect of your Onshape's data from a third-party system, but we'll talk more about that soon. And I also want to flesh out a little bit of that second architectural decision that I highlighted, which is feature script. So this is the coding language that is used for every standard feature that you see in the toolbar of any part studio. And the source code for that library of features is fully open sourced with an MIT license and just accessible through a public Onshape document. We like to say that any geometry in a part studio is actually just the output of a feature script function. So I love showing this little trick that's in the GIF to the right. If you click on any part studio at the bottom, if you right click on any part studio at the bottom, you can select show code and actually see this tab pop up on the right where the feature script that's actually generating your parts will show. You can even click on any part and it will highlight the section of code that's actually generating that geometry. Another very powerful advantage of this approach is a natural way to do configurations. You can think of a configuration as an input parameter to any feature script function. So they are much more accessible and flexible than in any other CAD system. Beyond this, anybody can create their own custom features and tables to help automate, analyze, and optimize their design processes. Commercial customers are leveraging feature script heavily to computationally generate their designs in much more efficient ways, and are even starting to hire developers focused specifically on developing their custom features and tables. So, one of the powerful implications of the database architecture and feature script is that Onshape now serves as a product data management or PDM system, as well as your CAD system. Because you no longer have to worry about files anymore, you can link parts and assemblies from any other document, including any public library of parts that has been shared as an Onshape document. This means you can very easily leverage design work that has already been done, rather than reinventing the wheel every time. Because of the cloud architecture, in real time, you can share and control the levels of permission with anybody using role-based permission schemes, providing an opportunity to understand how multidisciplinary product teams work together to create a full product. And release management workflows are also fully integrated into Onshape, allowing anybody to engage with the processes that are standard for industrial product design and development processes without worrying about all of the other different systems and integrations that would be required in a traditional CAD system. Another huge opportunity posed by the database architecture and feature script is an open REST API. For those not familiar, REST API stands for Representational State Transfer Application Programming Interface. And this is a standard protocol for almost any cloud-connected platform or IoT system these days. This allows anybody to directly integrate any computational workflow or a code-driven process with Onshape to optimize or analyze their design, or create a custom workflow or integration with any other engineering system. The REST API allows for you to securely access, add, or change any of the data stored in Onshape with those internal unchangeable identifiers that I mentioned earlier. And before we dive into some specific case studies and stories, I just wanted to highlight a couple of the types of computational workflows that we're seeing be developed. The first are automated processes for analyzing either document design data or user actions to help learn more about the models and how engineers are building them. And the second are automated processes for computationally designing parts, both using the REST API and feature script together. The two screenshots here are examples of these computational workflows that have been open sourced by researchers through GitHub, but I'll talk some more about these specific research projects soon. So now let's dive into how researchers are starting to leverage Onshape's cloud-native architecture in new and exciting ways. I'll highlight 3 different fields of research that are taking advantage of Onshape's unique capabilities. First, I'll show some examples of artificial intelligence and deep learning, where computer scientists are developing new algorithms that use Onshape's architecture to learn more about how CAD models are created. Next, I'll talk about the field of design process research and learning sciences, where researchers are using the append-only change-based data model to better understand how engineers are collaborating on designs and how students are learning about CAD. And finally, I'll show how robotics and digital twin researchers are leveraging CAD data in Onshape to add value at various stages of design and development processes. So to start, I wanted to quickly show this curve that I found while doing an overview search of dimensions.ai, searching for publications that use Onshape. As you can imagine, we're very excited by the trajectory of this curve. Of course, these publications include researchers who are using Onshape to create the kind of CAD models that can be made on any other platform. But I also think the exponential growth we're seeing stems from the fact that researchers are recognizing that Onshape is not just a platform for CAD, but a strategic platform for research. So the first example of research in the field of AI and deep learning is a project called DeepCAD out of Columbia University. These researchers have developed an automated process for generating and evaluating geometry using the REST API, and ultimately have open sourced their library of over 150,000 CAD models that they use to train their model so other researchers can use them as well. On the right side, you can see a randomized generation process that they use to create the 3D geometry using the language of CAD, sketch, extrude, sketch, extrude. You can imagine a potential application for this research is someday you can be able to recreate any imported 3D geometry with a list of CAD features that are then editable by engineers. Another exciting example of AI and deep learning research is this computer-aided design as language paper by DeepMind Group at Google in collaboration with an Onshape engineer. These researchers are applying algorithms that were originally designed for natural language detection to the language of computer-aided design, which are parametric sketches and features. You can see on the right a graphic showing how they can decompose a parametric sketch into each of its entities and constraints to understand how it is being created. A potential application for research like this is that someday you can have autocomplete or design suggestions for the CAD models in Onshape, just like you have autocomplete in Gmail when you're writing a message. Of course, these applications are still a little ways away, but it's very exciting to see how Onshape has enabled these new fields of research with CAD that were not possible with any other CAD system. The next field of research I'd like to highlight is design process research. This project comes out of the Ready Lab at the University of Toronto, where researchers are able to collaborate with one of Onshape's industrial customers, and we're able to look at over 1.4 million individual actions that 8 of their engineers made over the course of 8 months. All Onshape enterprises provide access to data through the analytics portal, where you can see high-level information about how much time engineers are spending on different documents, track how intellectual property is being managed, and other things along those lines. But the analytics portal also provides access to an audit trail, which shows a full history of all changes that designers have made, tagged with the user that made them and timestamped. This allows researchers to identify the different types of roles that team members are playing in this collaborative design process, looking at the amount of time each user was spending on different types of actions. They were able to distinguish between experienced designers, new employees, and reviewers working on the same team. You can imagine that team leaders can use these types of analyses to better understand how designers are working together and identify new ways to optimize the process using these new insights. Similar to design process research and commercial Onshape enterprises, learning science researchers are able to access the same type of audit trail information from an Onshape EDU enterprise. This is another project from the Ready Lab at the University of Toronto, where this master's student looked at how designers with different levels of expertise approached the same problem. You can see on the top an example of an experienced engineer following an organized design approach where they read the various drawings before starting the model, then follow a fairly systematic approach to create a sketch, adding features, and renaming or organizing their design as they went. On the bottom is an example of a less organized design approach from a novice designer, where they're jumping back and forth between editing features and sketches, and you can see from the top, they're only got through to the second drawing task by the end of their session. You can imagine an application for this type of research is to help teachers identify when students are stuck on a part of their design and notify them that the student needs support before they give up. And the last field of research I wanted to highlight is robotics and digital twin research. This example is from a student at Tufts University. He was able to easily model this self-balancing Lego robot in an Onshape assembly using the concept of linked documents, pulling part data from a kit of parts already designed in another public document. After designing the robot, he was able to use a specialized exporter service that produced a URDF file that included extra metadata about the assembly model to make sure that the mate information was stored in the exported file. Then he was able to use the model in an open source simulation platform called Gazebo to design and tune a control system for keeping the robot balanced. Once all of the gains were tuned properly, he was able to apply that control system to the physical robot and see the result. This kind of approach is not new for robotics, but Onshape allows roboticists to leverage their CAD models in new ways to add value at various stages of their development processes. In this case, using extra metadata from the assembly to export a smarter file for use in a simulation platform. And finally, I wanted to highlight this project coming out of the University of Applied Sciences Technikum Wien in Vienna, Austria, where researchers have developed a mini demonstration factory to have students engage in the powerful concepts of Industry 4.0 and smart manufacturing. In this project, they've started developing a way to use an Onshape assembly as their digital twin for directly monitoring and controlling their physical factory demonstrator. Using the REST API, they're able to integrate data from their Internet of Things system to directly update the assembly to reflect the current state of the physical system, and use user inputs in Onshape to control the physical system. Now, rather than using some separate application, you can natively use your Onshape assembly design to provide a spatially contextualized way of visualizing data in real time from the system, and a spatially contextualized interface for controlling the various parts in real time. And finally, I'd love to highlight some of the exciting ways that teachers in higher education are using Onshape to have their students engage with engineering practices that go beyond the basics of CAD. Of course, teachers are also leveraging Onshape's accessibility to teach more students than ever before the basic sketch extrude concepts of CAD, but I want to highlight the cases where teachers are having students engage in practices of collaboration directly from within the platform, using the built-in data management capabilities to show students real industrial workflows, and leveraging FeatureScript to have students learn more about computational thinking and design. The first example I wanted to highlight is from Memorial University in Newfoundland, Canada, where Professor Caroline Koenig teaches an Intro to CAD class for first-year engineering students. Professor Koenig pivoted to Onshape when her class was forced into remote learning, and she was able to continue having students be engaged by designing fun and creative assignments while learning the basics of CAD. But beyond the accessibility, she was able to leverage sharing and collaborative capabilities to have students engage with each other's design and learn about what it really means to work in teams and provide constructive feedback, arguably the most important kind of skill for an engineer to have. Another example of teachers leveraging Onshape to have their students engaged in collaborative design practices comes out of Technion Israel Institute of Technology, where they teach a technology education course for in-service teachers. The designs challenge for this class was to design and 3D print a strand beast walking mechanism in teams within Onshape. You can see an example of the students' work on the left, but what I love about this example is that teachers were able to leverage their Onshape EDU enterprise analytics to gain insight into how students were actually working together in their teams. Using these data, they were able to identify that each team of 3 had one team member doing a vast majority of the work. This has inspired actually some separate research, but also provided the teachers with an opportunity to discuss different ways that team members could contribute in a collaborative design project. Beyond Onshape's collaboration capabilities, teachers are also leveraging the built-in product data management features to have students engage in the powerful concepts involved in product lifecycle management. In this example, Peter Ebesmeyer from the Fraunhofer Institute of Mechatronic System Design in Germany is using the concept of linked documents and integrated bill of materials to teach his students about the difference between a manufacturing bill of materials and an engineering bill of materials, using an accessible and an engaging example of a Lego robot. Because Onshape is only running in the cloud, all of his students could get their hands on this document and see firsthand how the bill of materials can specify additional information about each part in an assembly, and even play around with adding custom properties themselves. Another great way that teachers are leveraging the native product data management features of Onshape is through team competitions. This example comes out of the Karlsruhe University of Applied Sciences in Germany, where students were competing in the 1001 Vela Cup. In this example, they had 30 students split into 6 different teams working on 120 different parts of the boat. But they were able to manage all of these moving parts directly from within an Onshape document. I like to say that with Onshape, the technology gets out of the way, and you don't have to worry about using any other system to manage your work. Everything can happen from directly within the document, and this team was then able to actually build and sail this boat during the competition. And finally, I wanted to highlight some of the ways that teachers and students are leveraging FeatureScript to engage in computational thinking and design. One of the awesome ways that we're seeing students engage directly is by creating custom features that are particularly useful in robotics competitions or digital fabrication applications in makerspaces. These students share their custom features as public documents through forums for others in the community to take advantage of their original design. On the bottom is a custom feature for generating standard parts for a robotic building system. And on the right is a feature script originally written by a grad student at Stanford University to optimize the layout of parts for a laser cutter to minimize material waste. Another awesome example of a teacher using FeatureScript in their class is this computational fabrication course at Boston University taught by Professor Emily Whiting. In this course, this is a course in the computer science department, actually, but they're using Onshape because of how seamlessly integrated and applicable the FeatureScript is to designs. The prompt for the final project was to develop an algorithm for producing a physical product. I love this prompt because students are able to take it in any direction they want and really show their agency in their designs. These images are 3 examples of student work at the end of the semester. On the left is an example of a computationally designed merry-go-round where the gears and the horses were all generated with FeatureScript. In the middle is an example of a hydroelectric attachment for a shower head, all again computationally designed and fabricated. And on the right is an example of a algorithm that will generate a mold for a tea infuser. So for any given shape, a snowman, a sun, a heart, a rectangle, you can generate the mold that will produce that shape into a tea infuser with the correct holes to make sure that the tea flavor actually gets out. So, in summary, what are the main takeaways from this talk? At the highest level, I hope that I've been able to show that Onshape is much more than just a platform for computer-aided design. It is a strategic platform that is being used by faculty members around the world for new opportunities in research and teaching. I started by showing how Onshape's cloud-native architecture is fundamentally different than any other CAD system and opens up a whole new world of opportunities for researching and teachers. Then I showed a number of ways that engineering and computer science researchers are integrating computational workflows to learn more about CAD models and leverage CAD data in new ways and for new applications. Finally, I showed how teachers are using Onshape to have students engage in real-world engineering practices that go well beyond the basics of sketching and extruding. And to finish up, I'd like to end with a call to action and ask all of you to get involved. Are you doing anything cool with Onshape that goes beyond the basics of CAD modeling? Or do you just want to learn more and be connected with any of the researchers or teachers I've highlighted today? Please feel free to reach out directly to me or to this edutech@ptc.com email address, and I would love to talk directly to you. And with that, I think we should have time left for some questions. Peter, have there been questions coming through?
Not yet, but while we're waiting, I'm curious to know, I think most engineering companies are still looking for engineers, to know how to use traditional CAD systems like PTC Creo or SolidWorks. If students want to get hired as a mechanical engineer, why do you think it's important that they learn Onshape?
I love this question. So I think one of the most powerful things about Onshape is that you can learn the skills that a company is really looking for. If you're a skilled engineer, you can very easily learn any new interface. But what companies are really looking for are engineers that have experience really working together and understanding how data actually flows through a product development process. So Onshape creates so many opportunities for you to engage directly with that from within the platform. The ability to computationally generate a part are skills that companies are looking to hire. So regardless of whether they use SolidWorks or Creo, these skills you learn by understanding how FeatureScript can be used to generate geometry can be very easily applied and pitched to any company that's looking for engineers that have the skills of the future, beyond the fact that Onshape is the #1 fastest growing CAD product in the market. So we want to prepare students for the future, not necessarily what's there today.
Great, thanks, Matt. I'm also curious to know, what do you think a student needs to know in order to learn how to code using FeatureScript or the REST API?
Yeah, it's a great question. So with FeatureScript, from any Onshape document, you can click the plus button in the bottom left and add a new Feature Studio to your document. And within the Feature Studio, there's a number of snippets that will automatically be added to your FeatureScript just from the top menu. So that's a great entry point into starting to write your own FeatureScript. Of course, understanding the basics of coding syntax and computational thinking are key to actually making useful things with FeatureScript and the REST API. But there are resources out there, and we're continuing to develop more to get more researchers and teachers and students engaged with these powerful concepts.
Thanks, Matt. That was great. A question did come in, is the show code option, and I think it means that can be used as a program option, available in Creo?
I don't know the exact answer, but I do know that Creo does not use FeatureScript, so there is no programming language necessarily that's exposable to see what's behind the design. So FeatureScript is entirely unique to Onshape, and that ability to see this open source library of standard features is, again, something that no other CAD platform has.
Great, yeah, that makes sense. Thank you. How about, can you talk a little bit about how students and educators can get started learning about the PDM, product data management, and PLM features in Onshape?
Yeah, that's a great question. So I think my first recommendation would be to click on all the buttons. Onshape has so many of these features that are exposed either on the right panel or in the top left menu through the versions and history. So just clicking around is a great way to get started and see what's available. But beyond that, I think my number one recommendation would be to look through the Onshape forum. There's a super engaged community that's super energetic about understanding what these new design processes and data workflows actually are. Onshape is the first product like it. So we're still understanding the best practices for actually managing data from Onshape. So there's, again, a super engaged community, always willing to help, even with the most simple question about how you export a model from Onshape, up to the most complex question about managing customized data workflows for enterprise or professional applications.
Great, thanks again. You know, I used to teach CAD at the university, and I'm curious, what are your thoughts about how Onshape can be leveraged for other courses besides just CAD courses in either the university or at the high school level?
Yeah, that's a great question. So I think the first example to point to is Professor Emily Whiting's course at Boston University, which is a computer science course. And because you have that feature script, students can immediately see the results of their coding in an actual useful product design process. But beyond that, Onshape is this hugely flexible and extensible platform for visualizing three-dimensional concepts. So you can imagine a statics or dynamics professor using Onshape to help their students visualize and understand concepts like roll, pitch, and yaw for an airplane and transformation matrices, or in statics, using stress strain curves of various objects in Onshape. So I think the accessibility and extensibility of Onshape as a platform makes it very relevant to all mechanical engineering disciplines, but of course, other engineering disciplines that need to understand the basics of what a physical product design process really looks like.
Great, thanks. So exciting. One other question, can you talk a little bit about what simulation is possible with Onshape, and particularly perhaps address why was the self-balancing Lego robot simulated in Gazebo?
Yeah, so within Onshape, there is at the moment no simulation capabilities. It's something we're working on, not yet sure what the education offering will be, but the simulation that will be in Onshape will be the most basic finite element analysis simulation. What that student was doing with the self-balancing robot was actually a physics simulation. So in order to tune that control system to keep the robot self-balancing, we needed to actually see what the force of gravity was doing to the robot and understand the ways that the motors were actually moving. So that type of force simulation is something that is not native within Onshape. There's a whole host of connected applications that have first-class integrations with Onshape through the App Store, such as OnScale, which offers free computing, cloud computing power to all education customers. So that's a great opportunity right now where you can directly export your Onshape model into their platform and run all sorts of simulations in the cloud.
Great, thanks, Matt. Great to know that those tools exist. That's it for questions. I think we don't have any more at the moment. We could wait a few more seconds to see if any more come in.
Great.
But I don't see any, so I think that's it. Thanks, Matt.
Great. Thank you all for joining.